So I guess most of the people already know, but just in case there is anyone who's here for the first time or something, well, this is a group. There is a self-organized group. It's a study group, and we used to meet every Sunday. Today is the first time that we do this session focused on beginners. And the workings of our sessions are basically we have a Discord channel where we organize everything. We meet in this case of the beginner lessons at 3:30 UTC time on Sundays. At 2 UTC time, we do the regular sessions where we are studying a different book. And we normally do one chapter a week, although that depends on the length of the chapter, basically, but we try to stick to more or less 90 minutes. So that's basically the summary. For this session, this is the first time that we are going to be doing a session on this book. We're going to be covering hands-on machine learning with Scikit-Learn, Keras, and TensorFlow by Aurélien Geron. And by the way, there is a debate because there is also this version, which is the PyTorch version. I'm treating them as if they are the same book, but I don't have access to the PyTorch because I don't have an account in O'Reilly, and the physical version of this of the PyTorch book has not been released yet. So if there is anyone who has access to both versions of the book and is aware of any difference, please let us know, because I only have access to the TensorFlow for the moment. And the idea is to stick to this. We want to do the PyTorch version, but as it's not physically released, we are going to start with the TensorFlow, and then we will see when we get to the second part of the book, which is where we start actually playing with neural networks. At that moment, we will decide. So for this session, we're going to start talking about fundamentals of machine learning, and it would be Anirudh. How's your name? Sorry.
Yeah, you spelled it correct.
Correct. So I leave you. Tell me if you can share your screen.
Sure.
You should.
I'm sharing it. Is it visible?
Yeah.
Yeah, great. So hello everyone, I'm Anirudh, and this is my first session as well, where I'll be discussing a chapter. So yeah, let's get started. So this is how the chapter looks like. First, we have some introduction. Then we'll briefly discuss about the applications of ML. Then this is a big part where we discuss about the different types of machine learning systems. Then we have challenges of machine learning. Then at last we have testing and validating. So I have my notes with me. Let me share that. So yeah, with example, one example is image classification, where we classify images, and convolution neural networks can be used for this. Another one is brain tumor detection, where we do semantic image segmentation, where each pixel is classified to determine exactly location and shape of the tumor. And for this, we can use CNN or transformers. So similarly, we have classifying news articles for, since it is text based. So we use NLP for this, but transformers work even better. So for now, we don't need to know about all these terms, CNN, RNN, transformers. This is just example. We'll be looking into them in future chapters. So yeah. Then we have recommendation systems based on past purchases. For that, we use ANN, which is artificial neural networks. So let's get started with types of ML systems. So ML systems can be divided in based on the criteria. There are three criterias. So, based on how they are supervised during the training and whether or not they can learn incrementally on the fly, or how they generalize. And these are not mutually exclusive, they can be a combination as well. So, let's get started with the first part, how they are supervised. So, here we have supervised, unsupervised, semi supervised, and self supervised. In supervised learning, the data is labeled data, means we already know that what we are going to predict. Wait, the mapping is already done with the unknown to the known. So the algorithm learns from it, and then it uh, predicts for the new data. This is usually used for regression and classification tasks. In regression, we have a target value to be predicted given a set of features. Uh, Example would be house price prediction, where features can be the size of the house, the location of the house, the number of bedrooms in it, and so on. With these features, we can predict the price of the house. In supervised learning, target and label is generally treated synonymously, but technically, target is used for regression and label is used for classification. And features are sometimes called as predictors or attributes. So this is some terminology we need to keep in mind. So difference between regression and classification is, regression can be used to predict any value. It can range from $100,000, or for house price prediction it can, or maybe $1 million. So any number can come between. But in classification, we classify between two or three or four. It is a limited number of groups that we can classify into. Maybe so let's say if we have a algorithm that classifies an animal into a dog or cat. So here we have two options: dog and a cat. So we have unsupervised learning. Here we have unlabeled data. So the uh, algorithm has to learn on its own to it doesn't have that mapping. So in previously, maybe we'll get the training data set might have some features, and it would say, let's say for first training example, the price of house is $50,000. For second given set of features, it is $100,000. But here we don't have that kind of mapping, and it has to find the connection on its own. So visualization algorithms are good example of this. They try to separate clusters and prevent overlapping in visualization. Another one is anomaly detection. Another example would be novelty detection. So in supervised learning, generally the training data set needs to be very clean. And for example, if we have 1,000 dogs, and if 1% of these represent chihuahuas, the novelty detection algorithm should not treat new pictures of chihuahuas as novelties. So that's why it needs to be very clean. Another example of unsupervised learning would be association rule learning, where the goal is to find the relation between attributes. Example, people who buy barbecue sauce also tend to buy potato chips. So in the supermarket, then they can keep these two things together. So that is one application of this. So next we have semi-supervised learning. Here it is a mix of labeled data and unlabeled data, but most of it is unlabeled data. So one example would be how Google Photos works. Uh, it recognizes that person A is in photos 1, 5, 11, and person B is in photos 2, 5, 7. So this is the unsupervised part of the algorithm where it is clustering. Now all that the system needs to do is to, for us, we need to tell it that who these people are. So that becomes the labeled part of it. Most semi-supervised learning algorithms are combination of unsupervised, and supervised learning. Here, example, a clustering algorithm may be used for grouping similar instances together, and then every unlabeled instance can be labeled with the most common label in its cluster. And once the whole dataset is labeled, it is possible to use any supervised learning algorithm on that. So next is self-supervised learning. It is an ML approach which involves generating a fully labeled dataset from a fully unlabeled one. And once the entire dataset is labeled, any supervised learning algorithm can be used. Example, if we have a large dataset of unlabeled images, we randomly mask a small part of each image and then train a model to recover the original image. During training, the masked images are used as inputs to the model, and original images are used as its labels. Although this self-supervised learnings are not the main final goal, but the resulting model may be quite useful in itself. Example, to repair damaged images or erase unwanted objects from pictures. But most of the times, model trained using self-supervised learning is not the final model. Yeah. Example, if final goal is for pet classification, if there is a large data set of unlabeled images of pets, we can start the image repairing model using the self-supervised learning. Once it performs well, it should be able to distinguish between different pets. That is, when it repairs a cat whose face is masked, it must know not to add a dog's face to it. Then it is possible to tweak the model so that it predicts pets instead of repairing images. The model already knows what cats, dogs, and other pets look like. So final step is to fine tune the model on a labeled dataset so that it can learn the mapping between the pet it already knows and the label we expect from it. So this was self-supervised learning. Also, we have reinforcement learning, which is a different thing, where the model learns based on the penalties or the reward system. It automatically learns that if a task if it gets rewards for it, then he remembers it and in future and does not perform tasks for which it gets penalized. So that was about types of ML systems based on supervision during training. Now another category is where they can learn or not learn on the fly. So here we have two: online learning and batch learning. So in batch learning, it is also called as offline learning. The system is capable of learning incrementally. It must be trained using all the available data here, and it takes more time and compute resources. The system is trained, and after that, it is sent into the production where it does not learn and only applies what it has learned already. A model's performance tends to decay over time because the world continues to evolve while the model remains unchanged. This is called model rot or data drift. The solution is to regularly retrain the model on up-to-date data. So you need to train the model on full data set, that is the old data set plus the new data, and replace it with the old data. And this is not feasible as data keeps getting big and will cost resources to every time train from scratch. Then we have online learning or incremental learning, where a system is trained incrementally by feeding it data instances sequentially, either individually or in small groups called mini batches. Each learning step is fast and cheap. It is useful for systems that need to adapt to change extremely rapidly, like example stock market. Also, it is good for limited compute resources. It can be used to train models on huge datasets that cannot fit in one machine's main memory, and this is called out-of-core learning, where the data is fed in batches. One important parameter of online learning systems is how fast they should adapt to changing data. This is called learning rate. A very high learning rate means system will rapidly adapt to new data, but it will also tend to quickly forget the old data. And a very low learning rate means system will have more inertia. Example, that is, it will learn slowly, but will be less sensitive to noise in the new data or to sequences of non-representative data. Out of core learning is usually done offline, that is not on the live system. So online learning can be a bit confusing name for this. A big challenge with incremental learning is that if bad data is fed, the performance will decline possibly quickly, depending on the data quality and learning rate. And if it is a live system, then the clients will notice it. The bad data could come from a bug, example, a malfunctioning sensor or a robot, or it could be someone trying to game the system. That is, example, spamming a search engine to try to rank high in search results. To reduce this risk, we need to monitor the system closely and promptly switch learning off. Example, possibly revert to a previously working state if a performance drop is detected. We should also monitor the input data and react to the abnormal data using an anomaly detection algorithm. So that was with online learning and batch learning. Then, based on how well this machine learning systems generalize, we have instance-based learning and model-based learning. In instance-based learning, it is as if the model by hearts the examples, and for new cases, it checks the similarities with these examples. And this is not a very efficient way. Then we have model based learning, where the system builds a model for the examples and then uses this model to make predictions for new cases. To check the performance of our model, we can use a utility function or a fitness function or a cost function. Fitness or utility functions tell how good is the model and we need to maximize it. And cost function tells us how bad the model is and we need to minimize it. Then we come to the main challenges of machine learning. First one is insufficient quantity of training data. This is very self-explanatory, as means machine learning systems tend to require a lot of data in order to work well and generalize well. Second point is non-representative training data. It means that the data should contain all the types of examples which we expect it to predict in future. For example, if we are planning to make a dog classification, then we need to feed it all the examples of dog breeds from Chihuahuas and Rottweilers, etc. If we miss few breeds, then in future it is possible that it might not classify the image of a dog as dog. So missing non-representative data is a bad thing. Then poor quality of data. This is also very self-explanatory. Then we come here comes irrelevant features. It is possible that few features are not contributing that much to the model, and it's better to remove them. And this comes under feature engineering, where we have feature selection and feature extraction. We can also combine few features together. Example, for house price prediction, if the length of the house and the breadth of the house, it can be combined together to create a new feature called area of the house, which is more relevant. So this all comes under feature engineering. Then another challenge of machine learning is overfitting and underfitting. For overfitting, the model is too complicated. So whenever we are training the data, the model forces itself to fit to all the possible data points, and when it forces, the model becomes too complex. And for this, in this we then it does not generalize well. Similarly, we have underfitting, where the model is too simple. For example, a linear model would be a too simple model, and maybe not much too useful. And to fix these two problems, we have something known as regularization. And if the more the regularization, the more it makes the model less complex. And for this, we have hyperparameters. So if a very high value of hyperparameter is used, the model will be too simple, and if the value is very low, then it will be complex, and we have to find the sweet spot where it works well. So now coming to the last part, testing and validating. So whenever we have trained the data, we also need trained the model, we also need to know how well it is doing, and for that we do testing. And it is common to use 80% of the data for training and 20% for testing, but it also depends on size of data set. Example, if the data set is too large, like 10 million instances, then maybe 1% for testing is more than enough to get a good estimate of how generalization error is. And then based on this, if we train a model and find that training error is low but generalization error is high, it means that the model is overfitting the training data. Then we have hyperparameter tuning and model selection. So one problem that comes with testing is that if we have only two batches of data, one is which is one used for training and other batch is used for testing, it is not a very optimal thing, because if we are tuning hyperparameters on test data, then the model is sort of adapting to the test data, which we do not want, because in when we are predicting the examples would be completely new. So to avoid this, we create a third set called validation set or dev set. So whenever the model is trained, it is trained on the reduced train set, and when we need to do hyperparameter tuning, then we use the validation set. And ultimately, when we are ready with our model and we have finalized it to use, then we can test it on the test set. So this gives a better picture of how the model would work on real data, and how it generalizes. Then there is something called as cross validation or a k-fold cross validation, where the training set is divided into k groups, and each one of these acts as a validation set. Then average of all evaluations is taken, and then we decide which model is better, so that there is no bias between the models. But the drawback of this is that we have to train it more number of times, and then compute resources would be higher. One problem can also be there, that there is a data mismatch. This happens when the data which we are trying to train on is a bit different from the data which we get. Let me explain with the example. For example, if we are building a model that predicts that classifies flowers, which are pictures of flowers which are taken from a mobile app, from the camera of the mobile. But let's say the data set contains images which are directly taken from the internet. So here the data is not very clean, and if we try to test on the test set, and if the error is low, then there is an ambiguity that why is the data the performance low. Is it because that it was trained on a data which has a combination of both images, that is which were taken from mobile or which were taken from the internet, or is it because the model is overfitting? So to uh, overcome this problem, one solution is to have another set called train dev set, which was coined by Andrew Ng, where we deliberately mix the types of images, that is the web pics and the pics that were taken from mobile. After the model is trained on the training set, we evaluate it on the train dev set. And if the model performs poorly, then we can say that the model overfitted. But if it performs well on train dev set, then evaluate on dev set. And if it performs poorly, then problem is coming from data mismatch. So this, then we need to improve the quality of data for this. And the last thing is no free lunch theorem. It states that no if no assumptions are made about the data, then no one model is better than the other, and you need to evaluate all of them to select the best one. But this is not possible, so we have to make some assumptions about it, and then we have to select the model. So basically it tells that there's no universal one model that can be used for all uh, types of applications. Yeah, pretty much done. This was the chapter.
Thank you very much. Pretty good presentation. I like that you used like a handwritten notes. Pretty classic.
Yeah, thanks,
Actually
Khalid.
helps
Thanks.
memorizing, right? While you do
Yeah,
that.
correct.
Yeah. So does anyone have any question about the chapter?
I don't have questions, but I'm going to, there were some questions at the end of the chapter, and the author provided solutions. If anyone wants to, maybe we can go over those now. And then I also provided some additional questions in the Discord that if anyone wants to go over, we can go over. Um, I'll just put that out there and just see how people react. This is Tom.
Yeah, let's see your questions. I mean, I remember that one of your question was about the no free lunch theorem, which also
Yes.
yeah, it also
Do
took
you want
me
to go
some
over
time.
do you want to go over my questions first, or you want to go over the author's questions?
Oh, you choose. Yeah,
Let me go over the author's questions, and then we can go over mine. Does that sound good? So I put question number one in the chat, and then I'm going to put a link to the solutions.
so the question is, how would you define machine learning?
Yeah. And I put a link on GitHub where the author answers those questions at the end of that notebook. So, Carlos, do you want to read the answer?
Okay, give me a second to open it.
I can read it. Well, yeah, why don't you read it? We'll just wait for you, and then I'll keep pasting the questions in after you read them.
Okay. So let's go for it. Okay, so the author says machine learning is about building systems that can learn from data. Learning means getting better at some task given some performance measure. Yeah, it goes in the line of the second definition that is in the chapter where it basically uses that exact wording almost.
Okay. And I'm thinking there are 19 questions, so there's quite a few. So, I'm just going to paste all the questions in so that people can see them, and then maybe on their own, if people want to, they can go back to them.
Yeah, I'm gonna read the second one and see if anyone wants to volunteer to give it a try. The second one is, can you name 4 types of applications where it shines, machine learning?
I'll throw in one.
Like
go ahead.
classification. Like for example, is it spam or is it ham? That's a great. I can look up the other ones. They're really good to look at. Let's see.
Yeah, I think classification is a big one, and it can be another example would be image classification. So you have an image and you're trying to classify what it is. Handwriting recognition is another one.
I think it's looking for like those 4 modalities: tabular, image, text, and one more.
I was in the other chapter. Let's see. Oh yeah.
One example discussed in the chapter was detecting brain tumors.
There's also text generation, which is a very common one from applications like ChatGPT and all of that. And code generation, which is like another version of the same.
Let's see.
Okay, so shall we go with the third question?
Yeah, I mean, if we want to continue, there are 19, so
Okay.
I'll let you decide whether we want to go over all 19.
Okay, yeah, the third one. Yeah, the third one is what is labeled training set.
That's supervised learning, right?
Yep.
That's kind of like the most basic type to a certain degree, because it's very clear cut. And then you can have other ways where there's no labels at all, and it just sort of does analysis and figure out like, oh, these are grouped over here and therefore this, and these are grouped over there, therefore that. And then you got categories between those two and so forth. It's pretty cool.
In label
Yeah,
dataset,
exactly.
the mapping is done already. What needs to be predicted and given what the features are.
Yeah, it always took me like some time to get my head around the naming of things, because when you listen supervise the word, it makes you think that during the training there is someone trying to see if the model is doing well or not. It's kind of what the word suggests, but it's more on a previous phase. When you're preparing the data set, you decide what's the right answer, and then you just gave it to the model, and the learning process happens without you supervising. So it's kind of probably weird naming, but it's what it is. Yeah.
Yeah, I mean, there's a lot of names are jargon terms too, and it's easy to forget, and you have to go back and read it again. You know, like semi-supervised learning. It's like, but I just look at that section again. But you gotta, ideally, you memorize exactly what it is, and you don't have to look it up. You know, that's the best way.
I always think of it as with supervised learning, you have the answers or the labels, and the labels are the doing the supervising.
Yes, I agree.
Yeah, exactly. So let's go with the fourth one. What are the two most common supervised tasks? Yeah, I would say that probably classification is one of those, because we also already mentioned like spam tasks and things like that. You always start with a data set where you say this is spam and this is not.
Can you hear me?
Yeah.
I'd say regression. Okay. The second one. Classification and regression.
Yeah, that's correct, right? According to
Okay. I can see the questions. In what channel we have them?
I have not posted the questions yet. I will post the questions in the Discord after this session. Right now, I'm posting the questions as we go in the chat.
Okay. Thanks.
the fifth question is, can you name 4 common unsupervised tasks?
Clustering, I guess, would be one.
The questions, by the way, just to interrupt you, they're at the end of the chapter under exercises, right? We're talking the same
Correct.
questions. Yeah, so
Yeah,
if you read the
every single-
chapter, you would come to it.
Yeah, exactly. They are in page 37. Yeah, I can think of clustering, like when you give it some data about, I don't know, your visitors, your web visitors, and it will basically tell you what groups are in those, like where did it would create the groups of where they came from and the languages that you speak or things like that. It would basically cluster them.
Is reinforcement learning as part of unsupervised learning as well?
I believe, and check me on this, I believe reinforcement learning is semi-supervised.
Unsupervised. Okay.
Yeah, I struggle a little bit trying to understand the semi-supervision and the self-supervision. I believe that self-supervision is basically when the labels can be inferred from the data directly, like when we, for instance, train an LLM and we have a paragraph and we start like we take just a part of the paragraph and hide the end so it learns what's going to be the next word and that kind of thing. So it is the whole text there, but we're hiding a part, or when we take an image and hide a part and make it generate the missing part. So I believe that that is self-supervised in a sense, probably. I would say that reinforcement learning can be a little bit of both, either self-supervised or semi-supervised.
Well, AI and things I'm reading online is putting it into its own category. So like I said, I could be wrong. So like Geeks for Geeks has an article and they put reinforcement learning in its own category.
Yes, I see here that in Geeks for Geeks, they are putting it as no supervision, and it learns from feedbacks. So we can say a part of a learning. It's not included either in supervised or unsupervised or semi-supervised. I will share the link in the chat.
Yeah, it makes sense because Anirudh said at the beginning that the three blocks that we studied in the first section to classify, these three blocks are like non-overlapping. So it's like a different family of
Yeah.
models. Okay, so let's go with the sixth question. What type of algorithm would you use to allow a robot to walk in various unknown terrains?
It's a reinforcement learning, basically.
Search algorithm.
Algorithm, okay, sorry.
I think you're right. Reinforcement learning.
Yes, but we should know which type of algorithm exactly in reinforcement learning. I think.
I would think it's a search problem.
Well, I mean, with the reinforcement learning, it creates a policy based on rewards or penalties. So it has an agent that's going to select the best policy and try to enforce those policies, right?
Yeah, it makes sense. Reinforcement learning, according to the author, that's the answer to the question. I guess in a way, reinforcement learning. I mean, I never used it. I only know the theory behind it. but I always find that it was related somehow to some kind of search, because it's always like finding the best way to go to a place, or the things like that. Like,
Yeah.
what if you want?
You can make serious money designing a framer. Here's how. You can sell premium to
Okay, so let's go with the next question. What type of algorithm would you use to segment your customers into multiple groups?
Oh, that would be like that's the one. Right? That's
Map, yes.
I if that can be unsupervised learning
Yeah.
because they got the clustering example right after that section. There's a little
Yeah,
diagram,
exactly.
figure
Clustering
1.8.
is the
I think someone has a lot of noise. Yeah, but it will be clustering mainly.
yeah, it's almost a definition of clustering, right? To segment into groups. So the next question is, would you frame the problem of spam detection as supervised learning problem or unsupervised learning problem?
Supervised.
Yes.
By the way, on those other algorithms, A star would be a good search algorithm, and K clustering would be for clustering.
Well, I'm looking at the answer, but my instinct was that if I was trying to do spam detection, I would build a data set of emails that were spam and not spam, and I would label them. So I would use a human to label them as spam or not spam, and then I would therefore say that that is supervised learning. Any questions about question 8? About what the type of learning that spam detection is?
Yeah, I think it's supervised.
Okay, so question 9, what is an online learning system?
That's a system that can still keep on uh, learning more information, even though it was already trained. So, like an example would be like it has some system like RAG or something. I would assume that it can still get more information.
I think spam detection would have like some elements of online learning so that it can continuously update based on your previous week's email.
My understanding is, online learning, it basically means is, can the system continue to learn from I guess new data or new information? And I think something I have to remind myself is it probably doesn't technically need to be quote unquote online, but just can the system continue to absorb new information?
That is absolutely correct.
And I think,
That's
and I could be
correct.
wrong, I think that means you're in some way training, either retraining the system from scratch or you're training it, incrementally. So maybe you use the most recent data and train a new model, or you somehow update weights. It may depend on the underlying algorithm, whether you train from scratch or whether you somehow update it. So I'm not an expert in using that term by any means, but that's my understanding. And I'll put the answer from the author into the chat as well.
I think it's kind of like, for example, the LLMs these days. For example, GPT, it's kind of continuous training, or we can say, I don't know the exact term. Maybe it's post-training, as it's continues to like train on other data, like continuously, rather than like to do like the training from scratch again and again. I think I might be wrong, actually.
Yeah, this category confuses me a little bit because to me, learning is like if you take any system that is not an online learning system and you start retraining it, it's with the updated data, it sounds like it's going to be a little bit more an online system, right?
No, because it's
So
not an incremental training. I think Tom defined it really well when he described it there.
Right. And now that I look at this answer, I think what it means, it's not that whether it's new data, are you training it from scratch? So if I get new data, but I train my model from scratch, it seems to me that would still be batch. I mean, yes, I'm getting new data, but I'm starting from scratch. So my
I
thinking
think
is that's batch.
I think the issue is that it's just defined in a very high level way without giving any examples. So ultimately, it was already trained, and if it can't learn any other way, game over. So it's obviously got to have a mechanism such as one example is RAG, but there are no examples cited as I can as far as I can see.
yeah, exactly. We have to kind of assume that learning means updating weights, because otherwise, if you use RAG every time that you make that you update the sources that enrich the petitions of the user, you are actually making the system learn in something. So it's kind of
But you didn't have to go through the training phase before. So there's a training phase, and that's sort of like very batch oriented, whereas the RAG is more dynamic. So I think that represents more of an online kind of ability to learn, even though it doesn't really. I mean, obviously, to really learn it should also keep that memory too. I'm sure the
Yeah,
modern systems are more that way.
but is RAG is it creating learning or just expanding the embedding space? It's not, you're not learning more, you're just providing a richer embedding space to provide an answer from an already trained model. That's RAG. We're in the
Well,
field of machine learning in general, and
you
what
have
we're
to embed
talking
it.
about is, yeah,
Definitely
but
have to
because you've
embed it.
embedded something, it doesn't mean you're retraining the model. You're just providing a richer source of tokens.
I agree. You're not retraining the model, but you're giving the model ability to, in an online fashion. It's no longer just tied to its original training batched files, right?
It
I
is absolutely tied to its original
Well,
weights.
some of it might be definitional, because this question is using the word system, not model. So even though you're not retraining the large language model, I'm wondering, well, are you sort of, creating an online system? So I don't know. I don't really see this term
Right.
much. I haven't used it
I think
much.
it's a
So,
good
is
point
it system versus model? Are you guys both correct?
because as a
Yeah.
system, for it to really learn, it should also remember.
Yeah, I don't know. I'm gonna.
Otherwise,
I would.
it's going to be temporary, and you reboot it, it's going to forget everything. That's not learning. So I think there's a system component there.
I think for this definition, no, that online learning refers to incremental updating of weights.
Oh,
Without requiring full fine-tuning every time, I'm guessing.
okay. So let's see. So it's like the fine tuning.
I don't think so, actually.
I don't know how you could update the weights otherwise. You'd have to do either training or fine tuning, right? So fine tuning is sort of, well, I don't know. You could look at it as batch too. It depends how you define the terms.
I think, as I've
Um,
seen here in this article of DataCamp, it said that we keep mainly the same weights, but we keep like the continuous learning on all the new data that we are receiving by time. That's what I've understood, actually.
Yeah, I think that is it because in the book we are reading, I also saw something like that, and I posted that section in the chat. Says out-of-core learning is usually done offline, and so online learning can be a confusing name, right? And it says we should think of it as incremental learning. So when I was reading it, I checked with ChatGPT. The book compared it with batch learning. So it's more or less like feeding. You don't give the system all the data, but the system learns the data as learns from the new data as it goes on. So it increments. Then with a batch learning, you give the system all the data you have, then you feed it with it. So you don't train it again afterwards.
Oh well, I just reviewed the. I think the issue is that it just doesn't do it in one huge batch, and it's designed more to do it in smaller increments. So it just depends how you define the terms. I think it's a little bit vague. So
I think
Yeah,
Not
in the
really.
article,
I mean,
I think
in the
I think
practice, it's pretty clear when someone's talking about online learning, what it means. You're just trying to apply it to large language models. But really, we're talking in general about machine learning, and amongst practitioners, it would not be unclear or vague.
obviously,
in the
it
article of
can't
the
be
data,
vague if you're going to implement it. It says right here. Additionally, online learning algorithms can be used to train models on huge data sets that cannot fit in one machine's main memory. So this is called out-of-core memory. The algorithm loads part of the data, runs the training step on that data, and repeats the process
Oh,
until
wait, we've
it
gone
has.
beyond online learning now? Are we on the
no,
next question? My mistake then.
That's
no.
okay. There's a section that's labeled online learning, and you just it's right. It's like right below the graphic.
Uh,
The online learning is useful for systems that need to adapt to change extremely rapidly. Well, we all understand that, like stock market data. It is also a good option if you have limited computing resources. And then it gets into that example I was just reading. I personally think it's not really fleshed it out as fully as it could. For example, by giving an example or two, it just sticks at that high level and doesn't really define its terms. But you can have a different opinion if you wish.
yeah, in the link that someone passed of the DataCamp article, there is a paragraph that says while both online and incremental learning processes data piece by piece, there are subtle differences. Online learning processes data in real time and continuously updates its model, while incremental learning processes chunks of data at scheduled intervals. So I guess it's not that different, but it actually means to update the weights, kind of the way I see it here.
I'm just wondering though, but I think other people disagree. It sort of suggests a little bit of that fine tuning idea, but the others disagree, I guess.
Yeah, no, it doesn't. If you think about what is fine tuning, what's occurring, and what is online learning describing. You know, online learning is describing, it's not an algorithm, right? It's the incremental updating of weights of a model as new data becomes available or may be necessary because of the size of the data. It's a constant, updating of those weights. That's not what's.
Well, it still does use the
Because
word algorithm though. It does additionally online learning algorithms ... I mean, that's obviously it's an algorithm. But
Yeah, something that is in
I
that
understand what
paradigm
you're
would be
saying.
called an online learning. But we're talking about what is online learning, not specific to the
what you're
algorithm.
saying is, I think I'm getting it. I think what you're saying is, it's not just going to be one huge batch. So it's designed where it just constantly keeps on learning by processing more data because there's going to always be more data coming in. It's an online responsive system.
yes. And
Right.
actually, it's not fine tuning, because fine tuning, it's you like adapt the model to a new task. But in the online learning, it's the same task, but you are just adding new data to the model and feeding it with the new data.
And both the training step and the fine tuning step are not really online per se.
Yeah, I guess with the last paragraph that I read before, my mind changed a little bit. Now I think that fine tuning wouldn't classify as online, basically because you normally would take like what we are doing in the book, in the LLM engineer book. We take some data, we decide what we want to do with it. So we prepare some batches of data, and we are gonna make the model pass over those batches a certain given number of times until we get the metrics or whatever, and we consider that it's ready. But I believe that the definition of online learning goes more with things like you're doing weather prediction, or you're doing stock market prediction or something like that, where you actually need to be training constantly. You cannot stop, because the day you stop, the quality of the model starts decreasing. So I
Yes.
think that's more or less the difference, or at least is what I'm getting, the idea
Yeah,
that I'm getting.
and actually we can think of an example that they cited here in the blog of DataCamp. It's fraud detection. For example, in fraud detection, we have we have always like new ways of like frauds or like attackers and everything. And if we don't like have that online learning, the system won't be able to know like what are the new examples and learn from them and predict something and predict that it's a fraud. So we can think about it how like this with the fraud example, because it's always something new and it always new methods. And yeah, they have like other examples like financial markets or healthcare as well. So we can, that's how I'm observing it right now.
That's a good example.
I put something in the chat. An interesting distinction they make is between random forests and gradient boosting. Where gradient of random forests is batch learning, while other forms of learning that use gradient descent is online learning. So the book does touch on it some there.
You're saying gradient descent is online learning?
Yeah, I'm just quoting from the book, so I'm not going to say much
I
more.
think it could be done either way. Gradient descent goes back to the earliest times, so I think it probably started as batch, but I think it can be done either way.
So we move on to question 10.
Yep.
Yes.
What is out of core learning?
Oh, okay. Let me see. I saw that right here. Yeah, out of core learning is usually done offline, not on a live system. So online learning can be confused. And it says, think of it as incremental learning. My phone's ringing. So let's see what it says. So right here, okay. So out of core. Oh, it says usually done offline, but not necessarily, because actually on the previous page, it used the out of core learning, and it suggested it could be done online. So let me look at a little bit more. 1 second. Right here. Interesting.
So basically, it can't store everything it needs to learn from in its memory. So it breaks up that very large set of data that it has to learn from into smaller mini batches and then processes each batch, one at a time.
Yeah, it says think of it as incremental learning. I think it just depends. Sometimes these concepts are very very important, and other times it's a terminology that it just depends on the context and how it's used in a real system.
I think I'm putting this in the chat. There is a warning about how confusing all these terms are. It's actually in the book, so I would say, I think it's probably good to know about all these terms, but we may not make it completely clear in this session. And the book clearly acknowledges that with its own warning. So just FYI. So I would say at least what I'm going to do is also try to understand what these terms mean and why the term was created. What is the purpose of understanding the term, or what is the underlying purpose for even caring if something is online versus batch versus out of core?
I think
Okay,
the way that I would approach
all
it
right.
is to think about, well, what's actually computationally occurring? What's the underlying process? And it's ultimately going to be based on some mathematical function that requires certain inputs. And so how is it handling that? And then what are the limitations of that system? So then it has to gather those resources in ways that we've come up with these terms to describe out of core, for example. But what's the purpose? What's it trying to do? What's the roadblock? What's the challenge?
I think that's a
the way
great
I would
point. And
understand.
is that Chris speaking? It's hard to tell who was speaking. Was that Chris?
Yeah, it's Chris.
Gotcha. Thank you.
Can you
Okay,
hear me
so,
okay? Am I sounding clear, or should I get off this headset I'm on?
You sound clear. It's
You
just
sound clear.
the
Okay.
Zoom interface doesn't make it easy to see who's speaking, at least for me.
I think
Yeah, so
this. Yeah, sorry.
This Emmanuel, I think with the out of core learning, the difference between the out of core learning and the online learning depends on the purpose. So what I realized was that with the out-of-core learning, we do it because the data set is too large to fit into the system's RAM. So then you chop the data into batches, then you feed it incrementally. But with the online learning, what I realized was that you do it because new streams of data come in. The data keeps updating. So when you leave it like that, the model will start decaying because it wouldn't have new data to work on, or to be updated, it's working on old data. So that is what I believe is the difference between the out-of-core learning and the online learning system.
For me, actually, this outcore learning, it doesn't have like something to do with online learning actually, because what I've seen here, it's the problem we don't have like enough memory. So that's why we use this outcore learning, and we try to break down the large data set and give it as many batches to the model. That's interesting.
So
Yeah, I agree. Actually, the article that you submitted from Saturn Cloud, it mentions out-of-core learning as a technique to manage data sets,
Yes.
more than as a training technique. So it's more about we already have a lot of data and we have to now chunk it or something like that.
Yeah, and there is another article of analytics. Yeah, I don't know how to pronounce it. Sorry. It said kind of the same thing, because we don't always have enough memory for the data sets, so we try to chunk it and give it to the models as mini batches.
Yeah, yeah. That's another good example is large language models themselves absolutely require out-of-core learning techniques because the data is too large.
So I had a comment and a question, and I guess it's both questions. So are these terms exclusive? In other words, can learning be both out of learning and online? And
You're describing two different types of learning. So one is describing a system issue, right? The lack of RAM. So therefore, you use an out of learning paradigm for it, where the other one is an incremental continuous learning of a model.
right,
Right.
I guess I know they're
So
describing different things, but can it be set up such that they're both, so that it's both out of
you
core
would,
and you're
in that
incrementally
situation,
updating the
then
weights?
your new data to learn from would be so large that each time you had to learn from it to incrementally and continuously increase or change your weights, you would have to then employ an a out of core technique. But it would have to be that large. Like every new thing that's coming in would be so vast that there was no RAM that could handle it so that you could process it. So I guess
Right,
so. Yeah.
and the point for asking the question wasn't whether it's actually done often. If you go down the track of thinking it has to be one or the other, then you're going to misunderstand what the terms are referring to. So the reason I bring up the point is to help us understand what the terms actually refer to. And you may have, and if you have a small device, a wearable device or other things, maybe there's some reason why, you're going to implement both, or there might be various use cases
I think, but
for
you would still,
implementing.
you would think about if you had a small device, right? And you needed to, do continuous learning on that small device. That's one thing that you're doing. But in order to perform that continuous learning, then you would use an out of core methodology. But you still, they're distinct definitions, if you will,
Right.
but they can both live together. You could be doing both
Right.
at the same time.
And that's the point I was trying
Yeah,
to, just to better understand the terms.
yeah, just as an example to add up to what Chris said. So let's assume you are doing stock market data on a device that does not have large RAM, right? The data needs to be current, it needs to flow in, but you also have a device that the RAM is very low. So you would have to chunk the data as it comes in, then you feed it into your system. So I think they can exist on a go.
Right. So basically, I think, if for nothing else, the term online learning in this context is a bit confusing. I mean, because you think of it as having to be online, that's all.
Well, I think online learning, like like that stock market action, even though it might take 12 hours to the next market day, it's going to get more data into the pipeline, so it really never finishes the training phase. It's just always going to process more data, right?
And anyway, I asked AI an example they gave, or a possible example that is both online and out of core, that they're giving is credit card detection. So if anyone wants to comment on that, and again, I have not verified that this is correct.
Well, so we're saying the
And would
out of
it,
scope is so big, right? That's the one that's really big, right? So it's got a.
right, so this is an example with the incremental updates, because you have credit cards
Mhm.
every millisecond. Every credit card transactions are happening every millisecond. But yet you do want to keep updating your model. So it's an example where the online learning might be done out of batch. Chris, would you agree with this example?
Would be done out of core, you mean?
Out of core. Yeah. So it is,
Yeah,
just to make
I
the
mean,
point that it can be both.
yeah.
Credit card detection is an example where something is both online learning and out of core learning.
Yeah, there you go.
And we'll go to the next one.
Cool.
Question 11 says, what type of algorithm relies on a similarity measure to make predictions? I would say anomaly detection comes to my head, because it's basically about comparing data, but I'm not quite sure, because clustering algorithms also rely in that case is on comparing distances more than comparing similarities.
No, I think you're correct in thinking about clustering algorithms, like k-nearest neighbors that rely on similarity to make those predictions. I think you're spot on.
I know off the top of my head, clustering is what came to mind for me as well. Cosine similarity. And I think there's probably more than one type of algorithm that fits in the answer here. The book mentions instance-based learning.
Yeah, okay, so the question was about algorithm type rather than specific algorithm, I guess. Okay, so question 12. What's the difference between model parameter and model hyperparameter?
So let's see,
I
what was the first one? I got the hyperparameter. Hyperparameter is a machine learning, in machine learning is a configuration variable that is set manually before the training process begins and controls aspects of how the model learns. Whereas the other one is you're accepting input into the model that is critical for the model to do something cool, like stock market data, different attributes that you want to use.
Yeah, I think of hyperparameters as for instance, the number of transformers in an LLM, basically the size of the model itself,
like the
or
architectural,
the learning rate. I would consider it also a hyperparameter. So all of the numbers that sort of define how the model is.
Yeah, I also think of hyperparameter as what the engineer sets for the model, as you've rightly said, and the parameters are what the model learns from the data after it has been trained.
Yeah, that's pretty good.
Is there, I'd like to hear from others, is there a sort of a gray area ever between if something's a hyperparameter or a parameter? And what I mean by that is, I can look at the function for an algorithm and it takes various arguments or various parameters, and I can specify the arguments for them. And if I say, well, I want to try, three of my options, I have three options, so I'm going to iterate through all three. I can go outside the training process and set up a loop to try all three of those or all three of those parameters. So in that respect is something within the training algorithm itself as the way I'm using it made it become a hyperparameter. Does that question make sense even?
Yeah,
Yeah,
I think it does
I like
make
your
sense.
approach. Yeah, I was just gonna say that I like making the question as approaching it as a gray area or possible gray areas, because at the end those are numbers, and if they are gonna be learned somehow, then we would call them parameters of the model, but otherwise we wouldn't. But I think that might depend. Let's say I'm prepared, my model is a grid of models, which sometimes with Scikit-Learn it happens that you can say, let's say that I'm doing a clustering of my visitors, of the visitors of my website. Normally the clustering algorithms, usually you tell them how many clusters do you want to observe. If you want to create 2 clusters, 3 clusters, or at least the number. So if I create a grid and I tell it, okay, make a grid from 3 clusters to 10 clusters, then that number, if I add a metric at the end so that it chooses the best one, it becomes like a parameter, right? It could be a hyperparameter, obviously, at the beginning. But if I do that, if my model is all of that, then it kind of starts being regular parameter.
Right. And yeah, and Chris was going to say something as well. I have another question, but I'll let Chris speak first.
Yeah, no, I mean, I think that when you think about parameter, right? Okay, so we all agree a hyperparameter is set by the engineer and occurs before the training. And parameters are set by the model itself. It's what's learned. The model learns the parameters. But when we break down the way that you're describing or what you're asking, and it's also a parameter that's sometimes called a design parameter. It's let's say the range in which a parameter must operate in. Does that make sense? That I don't think I think what you're describing is absolutely true, and that's set by an engineer. It's the design of the system. It needs to measure, you know, I don't know, temperature, and there's a set range, or maybe you know, Celsius versus Fahrenheit. You know, that's designed into, that's a parameter that's designed into the system, almost like a kind of a regulating parameter, but that's not the same parameter that the question is asking. So if I were thinking about it, I would think, well, what kind of parameter? There are parameters set by the engineer, but then there's the parameter that maybe the question is focusing on that is learned by the system itself. That's the kind of how I would look at it.
And I'll also point out, and this is maybe a subtle point, but the engineer can also use a hyperparameter tuning tool like Optuna and others, and grid search and Bayesian search, etc., to iterate through hyperparameters. So that they're not explicitly setting the hyperparameter; they're using a tool to kind of find the best one. My follow-on question is why do we make a distinction, or why do data scientists like to draw a distinction about whether something is a parameter versus a hyperparameter? Why is it important and useful to know the distinction?
It's like what Chris said. The hyperparameter is controlled only by the software engineer, but the parameter, which is part of the model, you do as the software engineer, you will decide what the parameters are, but then the tuning process, it decides the weight value, and all that's done through the
Well, but you can use an algorithm. My point is that you can use an algorithm or an automated process to also select and tune the hyperparameters. So
Yeah, but it's still an engineer's decision that that's the tool they're going to use to set those parameters, and that it's occurring pre-training. And I think that's an important thing. I think of hyperparameters as these tuning knobs, that I'm like turning. It's going to have it's going to be this deep. It's going to use this optimization. That's everything that I'm setting up so that the model then can start to train based off of all these hyperparameters that I, the engineer, have set up. And if I decide to use some, algorithmic technique to select where those knobs should be set and what knobs should be chosen, it's still my decision. I'm just using a tool to do my work because it's going to be perhaps better in whatever use case.
So your definition is the hyperparameter is decided upon or set prior to training, and that's what makes it a hyperparameter.
Yeah, it's all the choices the engineer makes. And I think, and this idea of knobs, it's not my idea. I was taking Andrew Ng's course once upon a time ago, and he was talking about it being knobs that you'd turn. I think it was Andrew Ng. It might have been somewhere else, but I'm pretty sure it was. That you're choosing all those variables that are going to, what's the size of your batch? How many batches are you going to have? What type of how many levels are or how many nodes are there going to be, or you're making all those choices, right? That's going to change the way the model then behaves, and that's kind of, when you talk about algorithms that do that work, because I've always thought of, engineers at some point having kind of just an intuition about what's going to work. I should just turn this knob this much because I know that's what's going to happen. It comes from experience, but then you can use optimizing techniques to really hone in on making those decisions for you. But you're still the engineer who's choosing to use an automation to set those dials and to even choose what dials to even have. I don't know. That's the way I think about it.
Why is it? Okay, I'll we can ask.
Go. What's your question? Ask what?
No. Well, why is it, important to understand if something is a model parameter versus a hyperparameter? And I guess, especially based on what you said and based on what I just put into the chat, which is basically the same as what you said, is the hyperparameter is something that can be chosen, while the model parameter is something
It's
the model
learned.
just it's something learned. Yeah, gotcha.
Yeah.
I have
And a design pattern a design parameter can affect, well, your choices on the hyperparameters are going to affect the parameters, but your design parameters are also going to affect how that model learns those parameters. I think there's that third distinction that really isn't brought up in the book is design parameters.
Design
I have a
parameters.
question. Is the parameters are like the hypotheses that like, for example, the engineer puts at the beginning and then like adjust by time based on the results of the model, or not? It's like the hypothesis that, for example, we have like k-means. Like the k either, like, for example, we put like randomly 3 at the beginning, for example, is this like the parameter, and then by time we find the engineer find out like it's 5, for example, and then the hyperparameter after it's 5 and the parameter is 3. I don't know if that makes sense. Because that's what I'm seeing. For example, that's what I'm seeing in the article. It said in classical machine learning literature, we might think of the model as the hypothesis, and the parameters are the hypothesis and that we put at the beginning, and the hyperparameters, it's the configuration that we find out or like we do after.
If I might say something, I believe that in general, you can name something parameter or hyperparameter once you have chosen an algorithm. Like, let's say that the algorithm is the simplest of one of all, linear regression. Then in a linear regression, let's say that we have just these two parameters, which is the slope and the bias. Okay, these are two parameters, and then you can have something like the number of layers or something like that if you want to have a hyperparameter. In that case, it's clear because we decided that the model is linear, therefore the slope and the bias by definition are going to be parameters because the algorithm imposes that. But in Scikit-Learn, there is this thing of the grids, and I think that we are going to see that in the next chapters. But something that I like about Scikit-Learn is that when you create something like a pipeline or just a succession of models or something like that, you always treat it like it's a model, and now you call it a model. But now it's not. If I'm using something more complex where I don't only have a linear regression, but I have linear regression and quadratic regression and something else, if now my model is do all of this and to choose the best one, I have a metric that decides, then there are things inside that became, in my opinion, parameters because I put them into an enclosure, and now my model is not a linear regression or a quadratic, it's a system that chooses between them.
Yeah.
I think it would be helpful to like hone in on, what are hyperparameters? Like, what's an actual hyperparameter? To put our mental model around it. And there's some things that are just like the quintessential hyperparameter, like the learning rate. What's the learning rate? And that's as we get further along in this book, we're gonna learn about the mathematically, what is a learning rate in a mathematical equation? Because what we're doing is we're implementing a mathematical equation with code using a computer to make those calculations, right? But ultimately, everything's coming from a mathematical model. So the learning rate would be the quintessential hyperparameter, or how large is your data? How much, how many training examples are you going to have in a single run of training, which is called an epoch, and it's called a batch, but the single run is called an epoch. So you may say, I'm going to have X number. You make that decision of how large your batch is, and then you're going to say, well, how many times do I want to go through all of these batches? Those are epochs. And you decide that as well, right? The more times it's going to be computationally more expensive, but maybe it'll produce more accuracy, or else maybe it's going to cause some other issues. Or when I say the depth of your neural network, how many hidden layers are you going to have, right? How many times are you going to run through calculations, or how many neurons are there going to be in each one of those layers? All of those things are going to, those are actual concepts that are that's what a hyperparameter is, right? Now, if you were to I'll just leave it at that.
I'm going to put something in the chat from the book that completely aligns with what you just said. And it points to regularization as a hyperparameter.
The what was it? The regularization?
Regularization, yeah.
The type of, whether you use regularization and the type and amount of regularization that
like
you
a dropout rate, for example, where you want to create a sparser embedding space, or yeah, exactly. Or the activation function, but that's it. We're gonna, we're further along in the book, we're gonna get these hyperparameters. We're gonna go deep on them. We're just kind of 30,000 foot view.
I just
really understand these things.
I googled it. I used Perplexity just now, and and I started studying the learning rate, and it's showing me the specific formulas, etc. So once you get into the math, it actually starts to make more sense.
Yes, exactly. That's what I meant earlier by if we understand, well, what's the algorithm trying to do? What's it implementing? It all goes down. It's all math. Even when we're talking about large language models, it's math. That's what we're implementing math. And if we understand, well, what part of the math are we using our vocabulary to describe, or processes that are necessary to make that math work? If we look at it that way, I think it will help our understanding of this book. Anyways, I'll try to always bring forward the math portion of it as we move along. I'll make that my effort, because I think that's really the most important thing.
Thank you, Chris.
Yeah, Chris, I think that will help. That will help.
Sure.
Shall we go
Do
for
we have
the next
another
question?
question? Yeah, that's all.
Put it in the chat. Carlos, you want to read it?
Yeah. What do model-based algorithms search for? What is the most common strategy they use to succeed? And how do they make predictions?
That's a tough question.
I don't know if I'm correct on this one, but from what I read from the book, I understand it's search for a general rule between the data set that was given. So it makes prediction based on the rule that it has learned that exists in the data set. I don't know if I'm correct on this one, but
Let me see.
I was just broadly, I was going to say we typically the algorithm will try to minimize or maximize something. So broadly, yeah, you're always either minimizing or maximizing some metric.
I think you know, it all comes down to exactly what you just said, Tom. Minimizing, but you know, to even give it more clarity, it's minimizing the loss function, and otherwise optimizing the model's ability to generalize on a problem set, so that you know, so when we do, for example, supervised learning, right, where we have the correct answer and the incorrect, or the question and the correct answer, and we run that through a model that learns, it sets these parameters, and it learns the best weights for these parameters, the best, you know, there are weights for these parameters, so that then when you have a similar question that runs through this model, it's going to generalize to that question that it might not have seen before. And the way that it does that is that you've minimized the loss function. I saw someone posted something. Hold on a second. Let me just see what. I think that was exactly right. Did someone just post something and it's gone? Never mind.
I think they posted gradient descent. Yeah.
Yeah, exactly. That is exactly right. That's so that would be the mathematical process of optimizing or minimizing this loss function, would be using gradient descent. That technique. Anyways, I don't know so did I explain that myself well there? Answering that question. What is it searching for? It's searching for, you know, minimizing that loss function to produce the greatest weights to generalize on other data. How does it make those predictions? And then you know, that was gradient descent. There you go. Look at that answer.
I put the author's answer in the chat.
Yeah.
So
Yeah, that's better said than what I said, but yeah.
Yeah,
I
I
think
like the yeah.
Oh.
I like the definition that Umaima said before, which was about the weights seen as sort of the generators of the hypothesis. So in a way, what it does is initially they used to be random, but what they do is they use numbers, which we call weights, to generate a hypothesis, and then via this thing that we call gradient descent, they have a metric and they know how good or bad they were, so they are going to go back and correct those hypotheses and do that in a cycle until they get the correct answer.
Yeah. Until the minimum loss function.
Yeah,
So.
exactly. And also, you know, going back to our earlier discussion on parameters, you know, those weights are being applied to these parameters that the model has come up with. But the model is very good at finding these patterns that we might not be able to recognize. Like we might not be aware, you know, of these nuances in this data. You know, large language models is a great example of this. There are things, you know, emergent behaviors that occur because we never realize that latent within our words is also logical thought processes that the model is able to recognize as patterns, and then create these parameters for those thought processes that, when something similar cause those neurons to light up, would result in a correct answer. It's much more complex than what I just said there, but you know, coming back to that thought about hyperparameters versus parameters, those weights are being applied to parameters. right? Those hypotheses. I like that as well. And then through gradient descent and back propagation, the model based off of let's say supervised learning, based off of the correct answer says, no, you got it wrong. You got to tweak you a little bit this way, and it does it over and over and over and over and over and over. How many times it does it over and over is a hyperparameter, because the engineer sets that and says, well, we're not going to do that over and over and over, a million times. Maybe the optimal amount of times is actually 200,000. Just throwing out made up numbers. See, that's a made up number, right? And those parameters, those would be relegated by the number of neurons in a layer and the number of layers that you have. So again, to give you a concrete example in computer vision, maybe your first layer would be the model's figuring out lines, different lines, right? And then maybe the second layer is figuring out combinations of lines. So you have geometric shapes. And maybe the next set of layers, which has a certain number of neurons, is figuring out combinations of those geometric shapes so it forms, a nose or eyes and so forth, right? But the engineer is setting those hyperparameters of how many times of that over and over and over I was describing. But ultimately, all of those weights for those parameters at those different levels, those different layers, are going to be tweaked and tweaked and tweaked until the model is more accurate. And so that on unseen data, it can apply those hypotheses and come up with a relatively correct answer most of the time. Yeah. That's all.
Okay. Next question. Can you name 4 of the main challenges in machine learning? I was going to make a joke, which was DATA, because it's data, the problem, but
That's absolutely right. Memorizing its data, it's not actually predicting new things. It's actually just memorizing the existing patterns in the data set you provided it.
Yeah.
Underfitted.
Yes.
Yeah, I'm not sure if this is what the author had in mind, but data snooping and data leakage, which particularly with certain types of problems like time series can be, or anything with a temporal component can be sometimes hard to avoid, difficult to avoid. You trying to use language models to make predictions. One of the big problems there is it's hard to build a language model at each point in time. So it's always, I think, an open question, as well as the language model just learning from looking at the answer, so to speak. So data snooping and data leakage, I think, is something that comes to mind.
Yeah, I just did a search, and the thing in my search said, lack of data, poor data quality, non-representative data, and then what Pat said, overfitting and underfitting.
I think that maybe it found the author's answer.
Yeah.
Or maybe the author was following that answer. Who knows? It's a big circle. It's a big circle. But
All about the data.
you almost, I guess another thing to add, and this is sort of taking a product manager's perspective, but a business perspective, is not understanding the problem that you're trying to help solve and not defining the problem. And I think, when we get to classification, we have all these metrics, and then they use the metrics to make new metrics. You have F1 and accuracy and this and that. But, in the end, let's say you're doing, credit approval, that can be done in a dollar amount. How much money are you going to make, right? And so I think one of the problems I see is that we stick to these vague and somewhat abstract metrics rather than defining a more practical metric. I don't know if that helped.
Yeah. Okay, so let's go with the next question. What is it? What is a test set, and why would you want to use it?
So the test set, oftentimes you have to do that 80-20, or, it depends, there's different ways you can divide up the test set. So sometimes you have to divide it more times than just that. But just classically, you got that 80-20 split. And then you need to do some tests on that training set to make sure, validate whether the data is good.
Yeah, I would define it as a part of the data set that you do not show to the model,
Right.
so that you can actually test that the model is generalizing well.
Yeah. Because you don't want the model to overfit, or to if you're always training it on all the data, then it's just going to memorize everything, and then you don't have a guarantee that it's going to do a proper inference to new data.
And a point I'll add in here is for it to truly be a test set, it can only be used once. So once you actually use the test set, you've sort of corrupted the process and you've peaked. And now and even if you say, well, I'm not going to teach that, I'm not going to let the algorithm see that, you as a human being, you as the designer, now have gathered some information that was supposed to be hidden, because this was supposed to be an unseen, sequestered test data set that mimics the real world where you just don't know the answer. So that's something just to keep in mind, and that is why we have the train and the validation and the test. Now the reality, if you have a huge data set, you can create multiple test data sets. That's no problem.
The
Sometimes
reality is that
when you
is
have smaller data sets, you have to make judgment calls about how you're going to handle everything. But
the,
it's something to
the,
at least be aware of. At least be aware of.
the data is really expensive. So I mean, we're talking millions of dollars. So I mean, ultimately, what would you do? Oh, well, just throw it all away. What? You just have to start all over from the very beginning. That's also expensive, because to do the training phase is going to cost a couple $1,000,000, perhaps, right? I mean, it's not trivial, but that would be the only way that you could use the data again. You would have to start over, tabula rasa, and just start from the very beginning, and that would be very expensive.
Right, and sometimes there's just not more data available. I mean, the data set's limited. So, if you're predicting something about the U.S. economy or the U.S. stock market, and you're specifically limiting it to the U.S. or to even more broadly, I mean, you may know, and this isn't always just mechanical. I think that sometimes this gets philosophical, and you just have to ask, what is it that you really know? Because you know what the U.S. economy did, right? You know that the U.S. economy, broadly for the last 250 years has been on a strong growth pattern, right? And I guess I would just say I think it's useful to not just mechanically create your train and test sets. Expand, right? You can do it, but with some questions, it's like you've already peeked at the data because you're a human being who has some awareness of the world. So that's just that gets more philosophical, but I think it is good to keep in mind and good to make sure you're being realistic and perhaps humble and moderate about what you really learn or what you haven't learned, and depending on the specific problem or the specific field, it depends. Anyway, I don't know if that makes any sense to anyone.
Okay, so let's go with the next one, which is next two questions are more or less related yet. What is the purpose of a validation set? In the chat, we have a suggestion, which is validation set helps you figure out the hyperparameters.
I agree with that. I think.
Yeah,
Okay.
right here it says the purpose of the validation set in machine learning is to provide an unbiased evaluation of the model during training in order to tune and optimize the model's hyperparameters.
There you go.
And I think, one thing that we should probably revisit is the idea of, why a validation set, why the test set, what are we ultimately trying to do, and what are we trying to avoid? We're trying to avoid overfitting. We're trying to make sure that the model learns the underlying patterns in the data and not the noise in that data, and not memorizing that data so that it can be applied to, in our case, the test data and generalize to that test data. But if it doesn't, if it's overfit, then what do we do? Well, how do we solve that? And we can solve that by getting more data. But as Patrick mentioned, it might be very expensive to do so, or Tom also said it might not exist. Or we can simplify the model. We can use regularization, which Tom mentioned earlier in our discussion. But all these different techniques. But through the validation set, those hyperparameters we could tweak them, before even applying the model to our test set. But the thing to think about though is what are we trying to do? We're trying to find those patterns that exist in the data. And that's what machine learning is so great at, is finding patterns.
And Chris, correct me if I'm wrong. We're trying to find a balance between underfitting and overfitting, right? Because if all we want to do is avoid overfitting, right, we can just forecast the mean and be done with it. So it's finding a balance
absolutely.
between the two, right? Yeah.
Absolutely. But yes.
What were you going to say?
I was
But
going to
you're most likely going to face an overfitting issue because you're going to start from like a
That's the
certain
tendency.
model.
Yeah,
Yeah,
it's the human instinct to try to get 99.99% accuracy.
I was going to say I often visualize the validation set as something to control an overeager model and a test set to control an overeager human being. We try to get the 99% result, and the held out set helps us avoid that.
Can you say it? So the first validation is for an overeager model, and the test set for an overeager human being. Oh, okay. I like that. Interesting. I'm gonna adopt that. And when you say an overeager human being, it's because they didn't make the changes that they should have through the validation set. Is that what you're suggesting?
No, they actually tried a lot more. They tried every model that they have, every architecture variance that they knew about. So in a way, like our models have more capacity to adapt to the data. The human has more capacity to adapt to the data you expose to him.
And the end result of them trying everything is that they just put too many bells and whistles in that model. Yeah.
And it gets a really strong fit to the training data or even to the validation data, but then it may not generalize to the test data.
So the validation data should have been the alert to that engineer to say, hey, calm down, buddy. You know, this model is it's doing a little bit too much. You need to, you know, rein it in a little bit. But they're like, no, I'm going all out. I want to throw everything in there. At least that's what I understand.
And this chapter is going to get into it, but cross validation is another topic related to all of this that is very helpful. So for anyone new to this, there's another technique called cross validation that the book will get into in a few chapters.
Sorry, I was muted. We have two more questions. One of them is still about training sets. What is the train depth set? When do you need it, and how do you use it?
I'll just say that this is a term that I don't see used that often. I'm just going to drop that in there.
I didn't quite hear the question.
It's in the chat.
Okay. Switch back to that. Oops.
It's basically what is the train depth set? I don't know if I understood correctly, but basically what I'm seeing in this chapter is that every single time that you have a parameter, that something that you are going to be adjusting, you are going to need to reserve some part of the data set to test that these parameters were properly tuned. So in the first term, we have the model weights. So obviously you cannot show all of the data. That's why we have the training data set, but then we have hyperparameters. So it's the same thing. There is another set of parameters. So we have to reserve another part of the data, because if you show it to the process that is tweaking the hyperparameters, then it's going to overfit to that training set. So you always, every time that you add a new parameter that you want to check, you have to get another part of the data set, to reserve another part of the data set.
So it's the validation set. What we were just talking about.
I put the answer from the author in the chat. And I'm curious with anyone who works in data, it's my impression that train, validation, and test data sets are terms that are often and commonly used. Have you seen or come across this term, the train dev set, before?
Not really.
I think it's more known as the validation set.
Right, that's where I was a little confused. And to me, it was almost like, well, we're going to create a second validation set that we're going to use first just to take a quick peek at things.
What does the author mean when in the answer when they say that you use a train set when there is a risk of mismatch between the training and the validation data sets? Mismatch means that.
I think my estimation is, say if you're trying to train a model on somebody who's driving in drowsy conditions, if his eyes are closed or not. If your training set has images of different races of people, but your validation set only, your train set has only black African Americans as the thing that it got exposed to, but your validation set has a lot of other races. So it can, in a way, get trained or take a hint that darker skinned people are distracted drivers or something like that. So I think that the distribution on your training set is they're trying to map it onto the validation set.
And just I'll say that this question and this term sort of confuses me because I don't really see it used often elsewhere. I don't think I even see it elsewhere in the book. One thing I will add based on the author's answer is, and again, this will be covered later in the book, stratifying your data. So when you're doing your data splits, when you're creating the train, validation, and test data sets, I think it's a useful practice to stratify based on the thing you're trying to predict. So based on the labels, based on the dependent variable. So that's something that just to keep in mind, and it helps ensure that I mean there are other ways your data can differ, but first and foremost you probably want your data to be similar across the thing you're trying to predict.
Yeah, the last paragraph in the answer of the author, it says if it performs well, obviously you are evaluating the model. If it performs well on the training set and in the training dev set, but not in the validation set, then there is probably a significant data mismatch between the training and the validation plus test data. So the way I understand it is basically is to check that the division that you made between the validation set and the training set is correct. It's a little bit confusing because the way I see it is data that the model has actually seen during training, but you're still using it to evaluate so that you see that the evaluation set is correct. So you want to see that the split was correct, kind of.
Yeah, I would personally, I would put, I might even email the author and ask him about this one. I put a big question mark next to this one. So I want to get too hung up on it. We can certainly look for resources on the internet and see if we find other people using this term.
I remember when I read it at the time, it mostly made sense, but it's like you gotta always get back into it and get that context going. So there's so many different terms. I don't always have to worry about every single one. It depends on the actual project you're working on, but it's obviously good to study because then you're sensitized to the bigger picture.
And I'll also point out, just for people who are new, the author uses this term dev and train dev. Those are the things we've been calling, and that are more typically, I believe, called validation. So when you see a dev set or a train dev set, I think more commonly those are called the validation set. And the author himself, I think, uses later in the book validation. So that the very first time I used this book, I was like, well, what the heck's going on here? You use this term on one page, and then, later in the book, you use a different term. And maybe there was a point in time where dev sets were something that people were calling validation sets, but I think, and I actually did this, I did a search and I asked AI, I think validation set is the more commonly used term today. You know, which when you're new to something, to have different terms for the same thing can be confusing because you don't appreciate yet that they're the same thing.
Yeah, I just pulled it up on Perplexity. Is a training dev set like a validation set? It says yes. A training dev set is essentially like a validation set, but then they're gonna go blah 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 blah. But the point is, yeah, there's some sort of parallel there.
Okay, so last question. What can go wrong if you tune hyperparameters using the test set?
You will get promoted because your results initially look so good, but then when your model falls apart in production, you'll get fired and
I think
you'll
that's
be
when
out
it's
of work.
overfitted, right? And it doesn't it's just trained on everything. It's memorized, but it's not ready to predict the real questions in the unknown world, you know.
Yeah, exactly. The answer of the author is basically that the model was already trained to optimize for that test set, so you're not actually using that as new data for evaluation. Okay, so we are done, I believe. So the only last thing, we have the questions. Wait. We have the questions that Tom asked apart from the author questions.
And I'm going to
So,
say, you know,
yeah.
I'm happy to stay on if people want to, but I don't want like we've already gone long. So if people want to discuss
Okay.
those, and if people want to discuss those in the Discord, they can. And these are questions, you know, that I myself came up with based on my own learning. And I think the good news is I put those into AI, and AI does a pretty good job answering most of them, I believe. But you know, I'm happy to talk about them now, but I just want to chime that in. Carlos can decide. Carlos, you can decide.
No, so good to me
I just want to
to
explain
keep.
how I came up with them. I came up with them because these are questions I myself came up with as I was trying to learn, as I still am trying to learn.
Yeah. Okay. Sounds good to me to keep the discussion in Discord. So that way we also have like some continuation during the week. So the only thing before finishing the call is if there is anyone who wants to volunteer for leading the next chapter, or at least part of it, because it's like 74 pages or something like that, if I'm not wrong.
Is it the end-to-end product or the machine learning landscape? No, I think no.
End to end.
I'm always willing and able. And there's more code, so it's going to be more interesting. And I think that's where the math starts getting into it, right? A little bit. Yeah, right there. 5, 6, 7, 8, 9, 10. Yeah, I can certainly do either the first half or the second half, either way.
I can do a half too.
So who wants to do the first half?
Okay, I will go with the first half next week.
Okay, I can do the second half.
But I just need to know where exactly the first half and
Oh,
because we have.
I don't know.
I just posted an outline of the chapter on the chat if you want, if that's helpful to you in determining.
On the chat. Okay, right there. Fine tune select. Yeah, interesting.
It's 8 parts.
Anyway, what I did last time when I almost did the whole chapter, but I just we did less detail towards my second, the second half, and then the next guy took it over. So
I feel like 1 through 4 kind of belong together. And then, 5, you've selected your model, then you do stuff with your model. That might be a good split.
Okay, yeah, sure.
good.
And this one, another thing, I shared the answers and everything we shared in the chat and the channel, but I left. Can you, Carlos, send the other answers from question 13? Because I stopped at question 12. If you check the channel, I shared all the questions and answers and the links as well. We shared in the chat.
Yeah, I will take a look at it, and at least put the questions in. The answers are already available in the notebook, so. Yeah,
Okay.
awesome. Thank you for putting that in. That's very helpful.
Huh.
Okay.
I want to mention another thing, and this has worked for me, and I know it's worked for other people I know. I enrolled in a course at Arizona State University, and you can enroll in their courses for only $25. And then I am able to gain access to O'Reilly. And I've put information about this in the Discord. And this is 100%, on the up and up. You're not doing anything sneaky. And they have a pretty good computer science course. So if you had to pick one of the courses, I thought the computer science course was very good. Just FYI. So I know people sometimes have trouble finding access to the books. Has anyone else been able to gain access to O'Reilly by enrolling in an ASU course?
I didn't try myself. And
Tom, what is the validity of that access? Because when I saw that, it said that for the semester it is valid.
Yeah,
How many months?
I don't have a good answer to that question. For me, it remains valid, and I took the course several years ago. I can't assure you that's going to be the case for you. I know other people who have enrolled more recently who have been able to also gain access. I don't know if they have a process of cutting it off at some point. I know they do have they have some self-paced courses. So the Computer Science 110 is in the self-paced version. I think you have a year to complete it. So I would expect that if this works for that $25, you get access to at least a year, if not longer.
So
But again,
Tom,
I don't know.
do you have like an email from them? And when you log in over at Safari, are you logging in through some sort of university authentication system?
You are, and I put links to it and all the information in the Discord.
And
And
you still have
basically, it's
you still have the email address from the university? I'm just
I
curious if
do,
you,
yeah, yeah.
oh, that's
And
cool.
I have access, by the way, through another university. So for me, this is all a wash. I'm just trying to be helpful.
Yeah,
But
no, that's really helpful.
yeah,
I
you get it online, and it's just like you're a student, just like you're a student. Uh, it seems to work. I tested it yesterday. It still works for me. I had other people I know, and the reason ASU, I think, has some really good courses. I like a lot of things about their online platform called ASU Universal Learner. I could go on and on about that. But
Yeah, but
what they have,
what a great what
they
a
have a
great thing.
bunch of courses. Yeah, they have a bunch of courses that you can enroll in for $25.
Yeah,
And they
and
used to be free. They used to be free, but they want you to have a little bit of skin in the game. And $25 is a modest amount.
then you can
And then
use
if
that
you,
email address to get discounts everywhere.
right, if you complete the course,
Yeah, exactly.
like your grade, you pay $400. If you don't complete the course or if you fail the course, you just walk away. And so you can actually complete like the first 2 years of a college degree for $400 a course. But again, you don't have to pay the $400 till you want the transcript. You initially you pay $25 and you get access to office hours and to tutoring. So you can actually get live one-on-one tutoring, on demand. You can actually sit in on weekly office hours with the actual professor. I actually called the professor in his office one time and he was real happy and eager to speak to me. So I'm not, I don't rep ASU, but I think it's a great
In
That's
which
program.
cool.
in which channel you put the links, please?
I think
The
it's in the
Discord.
resources.
Yeah. What's your
Resource.
other university?
No.
University of Chicago.
Okay.
I'm in an online data science program there. And in a prior century, many, many years ago, and many of you were probably not even born, I went to University of Pennsylvania. I have a
I was
very,
born.
I have a very nonlinear path.
I'm probably older than you. I'm at FAU. I'm the oldest student
Well,
there.
okay, well, let's stay in touch. I really, what are you studying?
AI. Yeah.
Okay, cool. Um, and hopefully I don't get into trouble for providing this information about ASU, but
I'm sure they want it. I mean, I think that's
I
fantastic.
mean, I'm not, I'm just describing the world as it is. I just don't want people to abuse it, but I don't see why it's an abuse. I mean, hey,
Well, when I graduate, I'm going to enroll there so I can get the student discounts still. I mean, you get some serious discounts for software as a student
Yeah, exactly.
and
If you
hardware.
you get it,
I
you
put a
get
link to my discussion in the chat. There are also some public libraries provide access, but that's much more limited. Um, but anyone else have questions? Questions or topics they'd like to discuss?
Oh, you
so
get
you're
Gemini
saying
for free? Cool.
somewhere on Discord you posted the information for Arizona University,
Yeah,
right?
and I just put the link into the chat.
Oh, okay, I see. Okay, right there. Okay, I'll check it out. It's worthy.
And my personal thought is that in everything we covered today, I actually think the understanding the process for model validation and assessment is probably the most important because it's sort of universal. So this whole train I know we spent a lot of time on it, but setting up your train validation and test data sets, that's sort of universal to almost everything else you do in machine learning. And it's something not done often enough in statistics. So I don't know if anyone ever took stats courses before. In stats, they have something called in sample and out of sample. But even in my current data science program, anytime we can have a course that's a stats course, I'm like, well, why aren't we creating, a test set? Yeah, you can like explain it, but So to me, it's a very interesting contrast between how stats is often taught versus how data science is taught. I don't know if you, Chris, have anything to add to that.
Oh, it's all stats to me.
Yeah. But do you notice that a lot of stats courses taught out of a stats department or by a stats professor doesn't do the train, test, and validation sets, or train, validation, and test sets?
No, I mean, because they're speaking in a much broader sense about statistics, where data science is very focused on the use of statistics for data science.
And then one of the questions I put in the chat, in the Discord, that, discuss inference versus predictions, right? I think that's an interesting concept to just be familiar with. And I think
actually, a great
statistician-
book is called Statistical Inference. It's a really fantastic book.
And statisticians, I think, often focus on inference, while machine learners and data scientists often focus on prediction. And it's good to understand the differences. I mean, and the two can go hand in hand. And when you talk about explainability of machine learning, then you're in many ways talking about inference. But I think it's useful to understand the two and understand that different academics and different people come at it from different perspectives depending on where they started.
Yeah, the book that I'm thinking of is called All of Statistics, a concise course on statistical inference. That's often.
I'm just spitballing here. I think oftentimes in statistics, we don't see this test train data set splitting because traditional statistical models didn't have the kind of parameters we deal with when we deal with machine learning and deep learning algorithms. Because this control needs to be there when you have more parameters, much more parameters. Or maybe I might be wrong.
ديال الفيديو جينيريشن اللي كتستخدم الذكاء الاصطناعي والدور ديالها في
Yeah, I think that partly explains it. And statistics does use the terms in sample and out of sample. But the whole idea of using train, test, and validation, you can use a regular regression model, a very traditional regression model that people used to hand code, I guess 100 or 150 years ago. So I think you need the train, validation, and test even more when you have lots of parameters and you're at more risk of overfitting. But you can certainly overfit a plain old linear regression model as well. So anyway, I mean, that's how I would say that. I don't think what you said was incorrect, but I do think even a regression model, a plain old linear regression model, to me it begs the question, like if I create a linear regression model and it gets a good fit and a good R squared and a lower MSE on the in-sample data, and that's what is often done. Oftentimes, statisticians only use the in-sample.
even though my heart rate is
But then it fails in prediction, then it's like, did I just memorize the data? Like, to me, it raises the question is, well, what happened? Why is it failing in prediction? And it could fail in prediction because the world changed and the data generating process changed. Or maybe I just overfit from the beginning, right? And so, I don't know, these are more questions I have. I don't know if anyone wants to chime in. I mean, we've already gone a long time, but.
I'm going to take off. I'll see you all next week.
I will leave it here.
Aloha.
Thank you very much, everyone.
All right. Aloha.
See you next week.